Hello, everyone. Good afternoon. All right. Okay, welcome back. So today we're gonna see if we can finish this chapter for transformer. Actually, it's about deep contextualized representations. But as I have mentioned a bit in a previous lecture, that term of the so-called deep representation learning is actually referred to by transformers nowadays. That's transformers is basically a very commonly used network architecture that have shown really good performance in a lot of NLP tasks scenarios. So the let's go back to the slide for this outline. Okay, so we have last time we have stepped from word embedding to the so-called Elmo model, and which is essentially two-layer and a multiple layer and a multiple bidirectional LSTM network, right? And the advantage of such a LSTM-based model is basically that it uses the context to determine the representations for each word learned. Okay, so that the meanings, the representations for each word actually encoded includes the information from the context words. It's not just the word. So the representation is a dynamic embedding, not just a static embedding. Okay, so this Elmo model actually, the disadvantage of it, if we're gonna compare it with transformer, is that speaking of model complexity, LSTM is not as complex as transformer, which means that it is not as that capable of modeling the context information as well as transformer, right? Because it's just LSTMs, but no, the LSTM itself also is not perfect in modeling long-term dependencies, and the nature of the recurrence mechanism makes it has its own problem. For example, in terms of training efficiency, in terms of vanishing gradients issues, for example. Okay, so the very first idea of not using LSTMs or other recurrence-based models is like developed by people who are interested in using non-recurrence architectures to tasks like machine translation. Okay, so it's initially started in the community of natural language processing, that people wish to seek more efficient ways to encode inputs, sentences or input sequences, so that no recurrence mechanism is required. And it turns out that in the year, actually the same year, 2018, that the so-called GPT and the first generation of GPT and the BERT model has been developed. But the technique that they based on transformer is actually something that comes before the year of 2018. Okay, so which is in 2017 that Google has already released such a new generation text encoding technique called transformer. Okay, so let's get into that. And we will use some of the similar charts as this one to basically describe what the model looks like from inside and why it is powerful in modeling text input. All right. Okay. All right. So these plots on the right is from the original paper in 2017. Okay. So it shows the basic architecture of a transformer model, which is originally used in that paper for machine translation task. So a little bit review of machine translation task, which is a sequence to sequence architecture, right? So given the source, right? Given the source inputs, you have some words handled by your whatever encoding model you have. It could be a recurrent neural network, for example. And then after you have got some encoding of the whole input sequence or input sentence, you're gonna use that hidden representation as the beginning point, as the start position, start of your decoding step, okay, which is to generate a sentence in a second language. Right. So, for example, if I want to translate a Chinese sentence into an English sentence, right? So this type of architecture is a typical encoder to decoder architecture. So there are two components. So as these plots indicated, the part here is the encoding one. Actually, I think I better use the same color. On the right, oops. Right, it is the encoding part, encoder part, okay? And on the right, which is the decoder part, okay? And what's shown within each box is just one layer of model. And because you see the n times, and n means there are multiple layers of the same architecture, okay? And within each box, okay, I think some of the terms that we are those that we are familiar with. For example, the feed forward. Okay, so the feed forward is nothing fancier than a regular neural network. Okay, so this is just a regular neural network. And the add and norm here. So these shortcut from this point to right here. So it is kind of the residual connection, right? In ResNet, right? Because we feed some of the, we make some part of the previous inputs to bypass the feed forward network and directly feed to the output, right? So there's an add and normalization. So this normalization, you can think of it something like a batch norm. And I think it's basically a layer norm, but which is similar to batch norm, okay? So it's not something brand new that we are not familiar with, okay? So I think the only tricky parts is the light orange part, which is the multi-head attention, okay? So these multi-head attention, I think it lies at the core of the so-called transfer model, okay? So it doesn't, so this type of model doesn't have any recurrent mechanism. So there's no RNN, no LSTM in it. So what's replacing the RNN LSTM is the so-called multi-head attention, okay? And it is an alternative way to encode the input sequence without using any recurrent mechanism, but it uses the multiple attention head to calculate the attention scores, right? So we're gonna go into the details for that. All right, so inputs is a sequence of words, and it is first converted into input embedding. So now the embedding is something also we are familiar with. So it could be the word embeddings that we download from that we initialize with the for example, the torch and embedding module, and we can initialize it with pre-trained word2vec or glove vectors. So it's just word embeddings, and that word embeddings is combined with something. So this is also something new. So the so-called positional embedding. Okay. We're gonna. I don't think we're gonna analyze the details, the technical details of how positional embedding is composed, but it is something initialized. So it is something illustrated by this sine or cosine wave. But it's basically some additional values added to the input embedding, which marks the position for each word. Okay, so this is a second alternative technique to replace the recurrence mechanism, right? Because there's no recurrent mechanism, but the positions for each word within the sentence also determines the meanings for that sentence. So we will need to use some different way, which is the positional embedding to indicate to encode the positional information for each word. Okay, so that input is fed into the building block. Okay, and this building block is replicated for n times, and the outputs from the encoder will be some very compact high-level representation of the whole sentence, and that representation will be used in the decoder. Okay, so we're gonna basically tear apart the model and dive into the details about how those different modules look like, particularly with focus on the multiple head attention box. All right, so let me go to the next slide. Okay, so this most of the charts I use here is from this famous post called Illustrated Transformer, and I think it has several follow-up poster by the same author, which is about illustrated, for example, GPT or BERT or other modern models. So I would encourage you to look into those different posts so that you can get more detailed information about the cutting edge technique in NLP and machine learning. All right, so basically these charts here on this slide is a simplified description of what a sequence to sequence machine translation model is doing, right? If you think of it as a black box in the middle, it converts the sequence within source language into some target language. Okay, and if we do a further decomposition, so this is what I have covered in the previous slide. We can have a bunch of encoders and a bunch of decoders. Okay, and if we're looking inside the encoders and decoders, there will be multiple layers of smaller modules. Okay, so within that encoder, the big chunk of encoder components is actually a stack of smaller encoders. Okay, and each of those encoder has an identical structure. Okay, but the key is that they do not share weights, which means there will be a lot of parameters. Okay, so say on the left we have 6 layers of encoder, right? So if say one encoder comes with 100K parameters, and then 6 of encoders will be straight 600K parameters. So that's a lot of, growth, the growth of parameters. Okay, and same for the encoders. And in the original paper for the first for the transformer paper, for the attention is what all you need paper, the connection between each encoder there's multiple connections to each decoder. Okay, so which means that the output from the last encoder will be used at each step of the decoding step. So the decoding occurs at 6 steps, right? The raw generation is used to decode some raw outputs, and that output is used to fit into the next decoder. But the same encoding inputs will also be used. Okay, so that also means there's some additional parameters associated. And let's look into each small box of this encoder. And as we have seen 2 slides ago, it's actually basically a self-attention followed by a feed-forward neural network. So here we neglect some of this residual network connection and the layer normalization, for example, right? We only keep the primary part, the main part, which is the self-attention and the feed-forward neural network. Okay. And feed-forward network is something we are familiar with, right? It's just a weight matrix with some bias, right? So the key really here is the self-attention. Okay. So basically, so if we want to summarize the function of this self-attention layer, it helps the encoder to to look at the words at the other positions in the input sentence, and use that positional information to shape to come up with a representation for a specific word. Okay, so if we zoom in further within that each smaller encoder, okay, so within the self-attention, there will also be very dense connections. By dense, I mean that for example, the first input word in Spanish, in this word, we have this some representation. So these can be the word embedding for the first input word, right? So that embedding vector is fed into the inputs here, and the second word is also fed into input here. So now the self-attention will output some internal representations for the first word. So the Z1 will be the intermediate or hidden representations output by the self-attention layer, right? For the first word. For the first word, I should use this direction. Okay. So, but the key is that when we are computing Z1, okay, the words X2 and X3 is also used, right? So you see the red arrows here. We not just have this one red arrow, right? But also we have the red arrow from X2 to X1 to Z1, and also X3 to Z1, okay? So it's a different mechanism than a recurrent neural network, right? So if it's recurrent neural network, then we should have X1, X2, X3, right? At each time step, we will have some hidden representations, right? Hidden representations. If it's a recurrent neural network, then in order to use X2 and X3 in compute the outputs at the first time step, we need to use a right to left, right? It's kind of reverse recurrent neural network, or a bidirectional, 2-direction neural network, right? So we should use that as inputs, and the A is fed into the second time step, right? And the A is fed into the first time step, and then it will be created as an output. Okay, so it's kind of, there's no recurrent mechanism here, but it's a direct connection from X2 to Z1 and X3 to Z1. Okay, but how do we do this connection? We will introduce the details as we see the slides next. Okay, so anyway, the dependencies between these paths can be described by the self-attention mechanism. Okay, so let's look at the details of how this self-attention is calculated. Okay, so this slide is about the motivation of why we need self-attention. Okay, so it actually makes sense from a linguistics perspective or from a common sense perspective, right? So for example, the sentence said the animal didn't cross the street because it was too tired. Okay, say when we try to have a computer to understand the meaning of this sentence, it may come across some ambiguity in interpreting the meanings for each word. For example, the word it, right? It's pronouns, and we need to figure out. It's easy for us, for human beings, to figure out what exactly the word it is referring to, right? But it's not an easy job for the computer to understand this, right? It could be the animal or it could be the street, because there are two nouns, right? Before the pronoun it appears, right? So we're gonna use as much information in a sentence as possible. For example, when we process each word, the self-attention model allows to look at other positions in the inputs. So it's looking for clues to help lead to better interpretation or encoding for the current word. So when the model tries to output some representations, right, for the word it, right, it needs to consider all the words, right? For example, including the animal and the street, right? It should assign relatively different scores to those different words. Like these scores are the weights, okay? And that mechanism should is the one we need, because that is a model that makes sense. Okay. So in the attention scores that we have put this sentence, the same sentence, into some transform model that is already trained, and we look at the attention scores and visualize the attention scores by these intensity of the color indicates the values of the attention scores. Okay, so if you look at the attention scores of the word it associated with all the other words in the same sentence, you can see that the animal actually has the highest attention score. It's a very dark value, a very dark color, right? So it basically explains how the attention score works. Okay, so this high attention score means that when we are interpreting it, the word the animal actually plays a larger role. Okay, the representations of the animal actually takes a larger role in the computation of the output for it. Okay, which is a stronger association if you want to understand it in that way, right? All right. So how exactly are these attention score is implemented? Okay, so here comes some details. Okay, so it comes with a lot of parameters. Okay, so the parameters here are three types. Okay, so the green one is the word embedding. Okay, so these are the inputs, and the three types of parameters are the queries, keys, and the values. Okay, so each word is assigned with a query vector, a key vector, and the value vector. All right, and that's a Q, K, and V for each word, right? For example, the input is thinking machine, right? The first one has its own Qs, own keys, and Q values, and similarly for the other words. Okay, so how we compute the Q vectors is to use some matrix, some weight matrix. For example, the weight matrix WQ is used to compute the Q vectors for the word for each word, right? We can basically use the matrix multiplication in this case, x1 times WQ, for example, because WQ is 4 by 3 and X1 is 1 by 4. So the results would be a 1 by 3 in this case, right? And the QW and the WQ has its own parameters to be learned. And the WK has its own parameter to be learned. And WV has its own parameters. So I think these matrices are shared across all the words, okay? So the same word, the different words will use the same parameters as inputs, and it will compute some outputs as the queries, keys, and values. Okay. So, and the next key step is to compute the attention score, and actually it's simply the dot product. Okay, it's calculated by taking the dot product between the query and the key. Right, so it's a mimic. It's mimic to the common database operation. Right, you have some query, you want to get the answers, and then you will take the query. So, for example, in this case, you want to know how important machine, the word machine, is to the word thinking. Right, so then you will take the query of thinking, which is Q1. To compute the dot product with the key of machine, which is K2, right? And of course, we also need to take the self dot product between Q1 and K1, right? So that is give us some normalized that'll give us some attention scores as with the output of the dot product. Okay, so we can use the relative size of those outputs of the dot product to measure how important machines is to the word thinking. If we have a third word, right, then we will have Q3, K3, and the V3, right? Then we need to use Q1 2 times K3 to measure how important the third word is to the first word thinking. Right, so that is how we compute, how we get the dot product, how we get the attention score. Okay, but attention score needs to be normalized. Okay, so there's some technical details, right? So like after we get the score, we need to divide it by such a dimension, and those are just mathematical, not mathematical, but the computational tricks, so that the outputs is within a reasonable scale. Okay, and as long as we know that this is just a way to normalize, right? We normalize it to a smaller number here, and then we fit into a softmax, which will give us some values that sum up to 1, which is a more standard form that we want, because that is a more reasonable way to measure the weight, right? We want all the weights sum up to 1. Okay, so in this case, we said that when we interpret the word thinking, we show that the calculation shows that the word itself plays maybe 88% in determining the meaning of itself, but meanwhile there's 12% determined by the next word machines. Okay, so that is basically how we can interpret the weights measured by the attention scores. Okay, and we can use these weights to compute an average sum. Okay, we need to compute the sum of the value vectors. Okay, remember we have a value for each word, and then we use that weight to compute the values weighted by the normalized attention score, which is this 0.88 and 0.12. Okay, and the results, right? So you see that the V2 has a lighter color, right? It's more transparent because we only use 12% of V2, right? And we use 88% of V1. So these two parts is added together with a weighted summation, and that will be the Z1. And Z1 will be the outputs to the next feed-forward neural network. Okay, so that is how we compute Z1, and also how we compute Z2 in a similar way. All right. So that is how self-attention is done in one detail, within one very short, simple sentence. Okay, so because that is a decomposed showcase, and in practice, everything will be vectorized, and I think that is the engineering detail, because we want the data to be stacked into tensors, and we want to the implementing model can handle matrix, can utilize matrix multiplications as often as possible to accelerate the computing, right? So in the case of the vectorized operation, like we can stack two words into a matrix, right? And we use that matrix to times the weights for the query, the query weights, and get a query matrix. Okay, so this Q is actually a stack of Q1 and Q2, and then so is the K and V, but now they are in a capital letter now because they are matrices now. But it is essentially it's just a stack of lowercase vectors, right? And V1 and V2, right? But with this matrix representation, we're able to organize the next computation really quickly. All right. So for example, the dot product between each query vector and the key vector can actually be conducted with this one step of matrix representation, right? So if you have, look at the Q1, Q2, Key1, Key2, right? It's just use this matrix multiplication. You are conducting basically 4 steps of a vector dot product between vectors. Okay, and you feed it into a softmax, and the score will be used to will be computed with the element-wise multiplication with the V, and the results will be the Z's. Okay, and the Z is also in the same compact format in the matrix. Okay, and the first row is Z1 and Z2. Okay, so these are just engineering tricks. So the whole representation is the output for the current self-attention layer, and the representations will be sent to the feed-forward network. Okay. Alrighty. So that's basically how one step of self-attention is used. Okay. So I think we're gonna talk about next is the term that's shown in the very beginning in the slide, which is the term multiple head, right? So you see, we only have introduced one self-attention step or self-attention operation, but in practice we will place multiple self-attention modules, which is the so-called multi-headed attention. Okay, and the motivation behind is straightforward, right? Because a word can attend to other words in different ways, or a word can have associations, can have different types of associations with other words. Okay, so for example, maybe some other words are semantically important, but some others are syntactically important, right? So the non-semantic, the word, the non-concrete word, say the verbs, the adverbs, well, verb and adverb may have more significant semantic meanings, but for example, like the word of, the, and, so these types of words, they also play syntactic roles in determining the meanings of each word. So there are different types of attention scores we should consider, right? So using just one attention head is not enough. Okay, so we'll need multiple attention heads. Okay, so we can think of this one step is the calculation for one attention head, right? So we will need to define multiple of such attention heads, which means we will use multiple sets for query, key, and value weight matrices. Okay, so the number of parameters increase insanely fast because we are using just too many so many parameters to model the to capture the information in the input sequence. Okay, so like we repeat these steps for multiple times, and in this situation we have two heads. For example, we have the attention head number 0, and attention head number 1, and they actually have separate weights. Okay, and the original paper, it uses 8 attention heads, which is a lot. You see, because each attention head will comes with its own W, Q, WK, and WV. Okay, so 8 attention heads means that we'll have 8 intermediate representations as the outputs for the attention head module. Okay, and that attention head is concatenated and with a weight matrix to produce some average outputs. Okay, eventually it will be normalized into the same shape. Okay, and that's condensed representation will then be sent to the next feed-forward network. All right, so that's the definition for multi-headed self-attention. Okay, so the example provided by here in the post is that if we look at the 2 attention heads outputs, you see that because we have seen previously show that the word "it" will attend to the word "the animals," right? Let me use a different color right now. Right. So first, if you look at the orange attention scores, that's from the attention head 0, for example. It will attend to the animals because the animals is which word is a word that it is referring to, right? But also, if you look at the second attention head in green color, it shows that the word tired, right, is also assigned with a very high attention score to it, right? Because this is a different type of importance, because it tired describe the status of the object that it is referring to, right? So these are also kind of related, symmetrically related. So you see, these different types of attention scores actually can be interpreted in the can interpret the linguistic knowledge between these words in a very clear way, right? All right, so the word "it's," the final representation for it will take some representations from both the word "the animal" and the word "tired" into its final representation. Okay, so yeah, that is basically why multiple-headed attention is important. Okay, so like, but when you have multiple attention heads, some of the heads are really not that easy to interpret in a straightforward way. Like sometimes the articles they are also paid with very high attention scores, right? So I think right now there are a lot of work going on to interpret the meanings of those attention scores, but it turns out that it's still in our field of study that is growing really fast. That people can have different theories, different experiments carried out to explain those attention scores. All right, and most of this work are done within the community of in combination, in collaboration between computer science and linguistics and cognitive science, for example, and psychology. All right. Okay, so I think we have dived into a lot of details of the transformers model. I think it's basically what have been covered here so far is the essence, is the core technical contribution by the transformers model. Okay, and if we look at the performance, compare the performance of such a attention-based transformer model with RNNs in terms of concrete NLP tasks. So you can see that the performance compared with RNN-based model is pretty significant in terms of machine translation. So this table shows the performance measured in for machine learning for machine translation tasks. So the higher blue score you have, the higher quality translation outcome is. So at least people would trust this score. All right, and the training cost is, if you look at the number of computation, okay, the flops is a measurement of number of computations needed. It's actually smaller than RNN-based models, okay, because there's no recurrent mechanism involved, so there's not a long back propagation through time, for example, to compute. So it's basically computations like matrix multiplication that can be quickly computed. All right, that's transformers performance. And the complexity in terms of running time and memory costs is also significant improvements compared to recurrent models. Okay, and when the input sequence length is n and it is smaller than its representation dimension d, then you can see that the self-attention restricted. Then per layer, in each layer, it just requires that r times n times d quantity. And the sequence operation is basically constant because there's no recurrent mechanism involved. Okay, which is good news for this new technique. Okay, all right. So I think after transformer is introduced, now we can wrap up everything in transformer and use it as if it is a black box model, which is similar to the so-called LSTM model that we are familiar with. Because honestly, within inside LSTM, it's also a lot of computation going on, right? LSTM is not a basic unit, but it's a composite unit, and we can treat transformer as basically something as an encoder to replace LSTM, and then we can apply the same technique of pre-training so that we can develop the so-called GPT and the BERT model. All right, let's enter the next slide. All right, so let's look at the architecture of GPT. Okay, so it's a product from OpenAI, right? And it's first developed for language modeling tasks. Okay, and the nature of language modeling is just to predict the next word from the previous word, and it's one directional. Okay, so the GPT as the task, as it decided, the function, the architecture is decided by the function, by the goal. So basically the architecture is one directional. You see, but there are multiple layers of transformers. Okay, so in this case, it's 2 layers of transformers. So the model will, so within each blue ellipse, it's a transformer. So within inside, it's actually a huge amount of parameters within each box of this, right? So the embedding for each word, right, will be fed into the inputs of transformer, right? And that transformer will be used, the output will be fed out to the next word in the future time step, okay? The embedding will, at E1, will also be fed into the next word, okay? So that is a one-directional architecture. And after 2 layers, the output will be used for the language modeling task. Okay. So if you replace these transformer layers with LSTM, then it's just a 2-layer LSTM model. Okay, one-directional LSTM model. Okay, and actually it's not 2 layers. Okay, it's the GPT model actually proposed the 12 layers. Okay, 12 layers of these smaller encoder module, which is the multi-headed self-attention followed by the feed forward, right? So it's just a one encoder here, but they use 12 layers. Okay. All right, and basically they designed such a model to replace LSTMs, and it turned out working out pretty well. And it has its own limits because it's one directional, right? Because it's only used the left words as a context to predict the next word. So it's in nature, it's just a language model, right? To maximize the probability of the next one given all the previous words and given the parameters. Okay. All right. So after the model is trained, it can actually be used to a lot of different tasks. Okay, so the whole thing here, after the model transformer model is trained, it can be used to plug into the green steps here. So the model will be used as some encoder, right? For example, given some sentences of text, right? It will if the task is to classification, right? Then the sentence looks like this, right? With some starting symbol, some extract symbol. It will be fed into the transformer, and the outputs will be some linear followed by softmax, for example, to classify, right? And the entailments, for example, it will comes with 2 sentences, which is premise and the hypothesis, right? And some the concatenated inputs will be fed into the transformer, and the outputs will be produced. And other similarity, multiple choice, question answering will be also can be conducted using this way. Okay. All right. So it's basically a people are using transformers, or you can call it GPT as well, to one-directional GPT model as a way to as an encoder, as a general encoder to encoding whatever text input you have. Okay. All right. Okay. So because the transformers have in this particular example, the GPT based the GPT model has 12 layers of transformer encoders, right? So typically people will use the final transformer blocks activation. Okay, it has like 12. If there are 12 layers, then we will basically use the last layer as the one to predict as the representation to predict some label for the text, right? But there are also some research going on showing that which layer is more informative in different type of tasks. Okay, so GPT is also a game changer in terms of our performances, right? In language modeling, in different natural language inference tasks, they have significantly better performance. So this is a measurement of accuracy, okay? And this is also accuracy scores, right? But you see, there's still some improvements, space for improvements, because it's not all type of tasks that GPT can achieve a very good performance. So yeah, when we talk about the limits, it's determined by the nature of the model because it's a one-directional. Of course, it will not utilize the context from both sides in predicting the next word. And in this sense, GPT is not as good as Elmo, right? But since Elmo uses a LSTM, which is a weaker transformer, which is not as a good transformer as transformer, which is not as good an encoder as transformer. So GPT basically still outperforms Elmo, okay? And on top of these limits, actually the next model that we'll cover, which is BERT, actually outperforms GPT in a lot of ways, okay? So that's where the BERT is from, okay? So BERT basically add multiple directions to each position, so each word, for the word in each positions as an encoder technique, as an encoding technique, okay? So with these very dense connections, the model, the representation learned by each transformer actually takes into consideration of all the words in each positions, right? It takes into consideration of each words, right? So the dense representation learned in such a way will be used not to train a traditional language model, right? Because the representations already, in the computation of the representation, they already see the future words, right? So it doesn't make sense to set a task that predict the next word. So the task that the BERT paper used to predict is to use the masked language model, okay? Which is not to predict the next word, use the previous word, but it is to mask some percentage of the input tokens randomly, and then predict only those masked tokens, okay? So it's like multiple directional, right? It's a two-directional multiple classification task. Say, for example, in 100% of the case, the word the Harry is replaced with some mask. In other 10% case, it is replaced with a different word. Other 10% case, it is remaining the same, for example. So this is just a showcase of the example task. And the second task, actually, the typo here should be fixed. It should be second task, right? It will choose the sentences A and B from the pre-training example, and the 50% of the time, B is actually the next sentence that follows A, and only for 50% of the other time, it is a random sentence from the corpus. So in this way, the sentence, the semantic relationship from between adjacent sentences is also learned. Okay. All right. So after the BERT is trained, it's similar to GPT. It can also be applied to different types of tasks. For example, like a sentence pair, sentence classification, question answering, sequential tagging, right? So in those tasks, the final layer outputs for the outputs from the final transformer encoder will be used as the outputs, and there's some special token attached to each output as well, right? So that is the class label used for classification tasks, okay? And there are some special tokens in QA answers that indicates the start and the end and the span of each of the two sentences, of the two sequences, okay? All right, and let's see if there are other details. Okay, yeah, performance-wise, BERT is a significant breakthrough it has made, and I would say these numbers are kind of old data, and now after BERT has been proposed, various types of improvements have been made to this model, and the state-of-the-art scores are exciting, and people have been beating the state-of-arts in each year's conferences, each year's new models. But I would say that they're still distance away, like building really general artificial intelligence in terms of that are able to understand the human language. So the success of BERT and GPT comes with the cost of spending time and money training large, huge, gigantic models. Those models cost time, cost energy, cost data, and to train, and it doesn't necessarily work well in all types of techniques or all types of tasks. There's still tasks that those models don't work out really in a satisfactory way. So yeah, it's something new, something exciting, but it's also something worth thinking about carefully, and worth about people need to calm down and think about the nature of such a technique and what is the cost of pursuing these paths to for future work, right? So if you want to summarize the not the performance, but the meanings of these game-changing big models, they basically creates a new paradigm in NLP and machine learning study. So it proposes, it comes up with this unsupervised pre-training plus supervised fine-tuning paradigm, which is that not everybody needs to train a model from scratch by their own, but you can usually pick some model from the others and put it into some adopt it to some tasks that only requires fine-tuning on the small data sets or on a small part of the model. Okay, so which is, I mean, I think it's a reasonable way to share resources to create a sustainable environment for sustainable technical environments in terms of cost efficiency. Okay. All right. So yeah, the issues is something that I want to mention here. The number of parameters is insanely big, right? Nowadays, those models getting pre-trained is like basically hundreds of millions or even billions, tens of billions models. Those models is really expensive to train and doesn't make sense for everybody to train a model from scratch, right? So there's research going on to study the environmental cost, like how many electricity and how many carbon dioxide that you will generate if you spend that amount of time to train the model. Okay, so that's really a lot of cost, right? If you think of training a model your own, right? To pre-train a model like a basic transformer model, that will cost that many money, which will takes that much of a time to train on a server, and which also requires like GPUs, a lot of GPUs. Okay, and those other GPT-2 tasks, for example, it's even more expensive to train, right? You will need a stronger and stronger hardwares to support your computation, right? So yeah, so it makes sense to me that the trend is here. That's basically the big techs runs the resources. The big techs owns those TPUs, right? Google owns the TPUs, and the academia actually needs to adjust themselves, needs to make adjustments. It doesn't make sense to pursue into this direction. That's by stacking more parameters, by building larger models, you will beat the state of arts. So it doesn't look to me a smart way to go. Well, it is smart, but it shouldn't be the only way to go. All right. Okay, I think, yeah, that is the last slide. And I think that's pretty much for today. And for the homework that I'm gonna release tonight, I will have a homework for embeddings, for word embeddings, okay? But it's not about the transformers. It's not about the deep contextualized models, okay? So I decided to only have some quiz questions about these deep contextualized models, about transformers, about GPT or BERT, about some of the technical details. Yeah, but because it's very hard to design a programming homework that are suitable for these big models. So I'm still thinking about that. So, but for today, it's for sure there will not be homework assignments for the transformer chapter. Okay, but there will be one homework for the word embeddings. Okay, which I will release today, and it will be due in next Friday. Okay, so next Friday will be our last. I mean, the